Now that we've discussed a little bit of an introduction to fluids, we're going to take a closer look at the properties of those fluids and how we can describe them. And we're going to start by looking at the continuum assumption. Now, a real fluid is composed of molecules, and statistical models look at the interactions between those molecules, and then the behavior of the fluid is determined from probability and statistics. Now, this is very useful for understanding the properties and behaviors of the fluid, but it's not very practical for engineering applications. Here we're looking at things like statistical mechanics or the kinetic theory of gases. Our experience of a fluid is much different. So we typically think of fluids using the continuum approach, where we ignore individual molecules and we treat a fluid as a continuous substance distributed in space. This is much easier for us to understand. It's more like our own experience, but it requires that the length scale for the flow is much bigger than the mean free path of the molecules, which means molecules aren't going to just bounce from one side of our control volume to the other. This means that there's enough molecules at a point to provide a meaningful average, where we consider a point to be the smallest unit of interest, the smallest volume of interest. So if we consider a thought experiment in the second figure on this slide, if we want to measure the density of the fluid in a small cube with side length of L, the bigger the cube is, the more molecules are in the cube. So the local density is going to be the mass of all those molecules divided by the volume of the cube. At large length scales, when L is very big, we actually have pretty poor resolution. We're looking at a large area, so we lose information on the spatial changes for density. However, if L is very small, then there's only a few molecules inside the cube. So if we have one or two molecules leave the cube, it makes a big change in density. So what we want to try to do is to look at the intermediate regions. We want to look at the density over a small control volume where there's enough molecules that we can get a stable average, where one or two molecules isn't going to make that much difference. But we want to be able to have good spatial resolution so we can get the density at different points. Now, one consequence of the continuum assumption is what we call the no-slip condition. The no-slip condition basically says that you have to have the same velocity at the wall as the wall has. So if the wall is not moving, if it has a velocity of 0, then the fluid at the wall has to have a velocity of 0. If the wall is moving at 1 meter per second, the fluid at the wall has to have a velocity of 1 meter per second. This no-slip condition is valid for all real fluids under what we call normal conditions, when we have a valid continuum assumption. Now, whether that's true or not is determined, again, by the Knudsen number. So the Knudsen number is the mean free path divided by the length scale of the flow, for instance, the diameter of a pipe. And if we actually look at the kinetic theory of gases, we can relate this to the Mach number and the Reynolds number, and we'll talk more about the Mach number and Reynolds number later. So if the Knudsen number is less than 0.01, we have a continuum flow. So the continuum assumption is valid. If it's less than 0.1, we have what we call a slip flow, which looks like the middle figure on the left here, this one, where you have some slip near the wall because you have very few molecules, but still you have some version of the no-slip condition applied. And then if the Knudsen number is more than 3, we have free molecular flow, where we essentially have complete slip and we no longer have a valid no-slip condition. The slip length becomes basically infinite. In air, the mean free path is about 3.7 times 10 to the minus 5th centimeters. So for the Knudsen number to be 0.01, the length would have to be 0.037 millimeters. So what that means is, for air at atmospheric pressure and temperature, any system with a length, a characteristic dimension, larger than 0.037 millimeters would satisfy the continuum assumption, which is pretty much going to be any engineering flow of interest to us for this class. Now, there's a lot of different fluid properties. Density, of course, measures how much mass there is of a substance per unit volume. For instance, the density of water at 4 degrees Celsius is 1,000 kilograms per cubic meter. Now the density can vary a lot with temperature. However, in liquids it does not vary much with pressure. It does, however, vary for pressure with gases. Now, we have some idealizations. We can look at the assumption that density does not depend on pressure. For instance, as a liquid, we call that substance incompressible. So many liquids can be approximated as incompressible. However, it requires that the temperature be nearly constant and the Mach number be less than 0.3. That allows us to make the assumption of incompressible flow. Now, there's a couple of different versions of gravity, of density. The first is specific gravity, which is basically the ratio of the density of the substance to the density of water. So you take the density and you divide by 1,000 kilograms per cubic meter. And then the specific volume is how much volume a substance occupies per unit mass, and that's just 1 divided by the density. Now, pressure is the force per unit area on a surface, but it's always acting inwards on the control volume. So it's the force per unit area acting into a surface, or normal to the surface. It is a scalar quantity. It doesn't have any direction. And it's basically caused by molecules colliding with surfaces. When a molecule hits a surface, it has to change its momentum to bounce off, and that requires a force. And that force is the pressure. Now, absolute pressures are referenced to a vacuum. So there's no molecules, which means there's actually zero pressure. Atmospheric pressure in absolute pressure is 14.7 psi, or 101.3 kilopascals. Now, gauge pressures are pressures referenced to atmospheric pressure. So it's the difference in pressure between your measurement and the atmosphere. So, for instance, the gauge pressure of the atmosphere is 0 because we're referencing it to itself. However, if you look at a bicycle tire that's pressurized to, say, 30 psi, that's usually gauge pressure. So it's 30 psi gauge pressure or 44.7 psi absolute pressure. Temperature measures the energy of a substance. So objects with high temperature, for instance, transfer heat to objects with lower temperature. And two objects with the same temperature are in thermal equilibrium. And we have two kinds of temperature scales. We have 2-point scales like Fahrenheit or Celsius, which are basically based on the freezing and boiling points of some substance like water. Or we have absolute scales like Kelvin or Rankine, which are based on thermodynamics. And these are the ones we're going to use for most scientific purposes. In fact, we're almost always going to use Kelvins or Kelvin or Rankine for engineering calculations. For instance, the ideal gas law, when we talk about heat transfer in the next semester. Now, it's important to note the ideal gas law. The ideal gas law is what we call an equation of state. It describes the relationship between the properties of a substance, in this case, the properties of an ideal gas. So in here we can see we have a relationship between density, pressure, and temperature. Now, pressure and temperature have to be absolute quantities, so absolute pressure and the temperature has to be Kelvin or Rankine. And then R is this ideal gas constant, where we have a universal ideal gas constant and the molecular mass of the gas. The vapor pressure, very quickly, is the pressure of a liquid. Above the vapor pressure, the fluid remains a liquid. So if the pressure is higher than the vapor pressure, you're going to remain a liquid. However, if the vapor drops below the vapor pressure, we have the fluid start to vaporize. And then the vapor pressure actually increases with temperature. So for instance, at low temperatures, say 20 degrees Celsius, the vapor pressure of water is very low. However, at high temperature, the vapor pressure of water is higher. So the vapor pressure just tells us at what temperature something is going to start boiling or condensing. Boiling occurs when temperature increases above the vapor pressure, like boiling water on your stove. This is due to heat transfer. Cavitation or flashing occurs when pressure drops below the vapor pressure at the temperature of a fluid. So it's not due to heat transfer. It's simply due to changes in pressure. And this can actually be very violent. It's very bad for pumps and propellers and things like that. So the Navy is often very concerned about cavitation. Dynamic viscosity represents the internal friction within a fluid. It measures the resistance of a fluid to flowing, and it's due to collisions and attractive forces between molecules. As with other properties, it tends to vary with temperature. It changes depending on the temperature. Now we have some idealizations here. An inviscid fluid is a fluid with zero viscosity, so it doesn't resist flow at all. It's a useful idealization for some problems. However, most problems are not going to be truly inviscid. So we can get estimates from inviscid flow theory. However, we have to understand the limitations of those models. An ideal fluid, then, is one that's both incompressible and inviscid. It's ideal because it's easy to analyze, right? It has ideal behavior. The kinematic viscosity is also frequently encountered in fluid mechanics. It measures how rapidly momentum diffuses through a substance. And we'll talk more about that later. Then we can look at stress fields. Now, forces on a fluid can either be body forces or surface forces. Now, body forces act throughout the fluid, and they're usually a function of mass, like gravity represents a body force. Surface forces act on the surface of a particle, and those surface forces can either be shear stresses or normal stresses. Viscous stress or shear stress is typically related to the deformation rate of the fluid, so it's related to essentially du dy, the velocity gradient. This is basically the strain rate rather than the strain. Normal stresses, however, are due to pressure or compressibility effects. So then we have this stress tensor, where the taus represent shear stresses and the sigmas represent normal stresses, usually due to pressure. In a Newtonian fluid, we actually have a relationship between shear stress and deformation rate. So we have the dynamic viscosity, which defines the relationship between stress and shear rate or deformation rate. Now, when we look up fluid properties, we have to be a little careful. We usually find them in tables, and there's many tables in the back of the textbook. We need to take the time to learn how to read those tables. Now, it's easy if we have a condition that's in the table, we can look it up directly. However, sometimes we need to find the property at some value in between the values listed on the table. So we need to interpolate. We usually assume that there's a linear behavior between the two values. So for instance, if we need to find the viscosity at 22 degrees Celsius, we go to the table and we see 22 isn't here, but we have 20 and we have 25. So we take 22 minus 20 over 25 minus 20, and we assume that that's equal to mu at 22 minus mu at 20 over mu at 25 minus mu at 20. And we can solve this equation for mu at 22 degrees Celsius. So that's usually how we compute these types of things. The last thing to talk about for this discussion is the Reynolds number. The Reynolds number allows us to estimate the effect of viscous forces. You can see the definition of Reynolds number is shown here, and the numerator represents the inertia of a fluid, and the denominator represents the viscous forces. So this is inertia divided by a force. And in this case, it tells us how important viscous forces are compared to the flow's inertia. If the Reynolds number is very large, then viscosity is much less important than inertia, and we may be able to assume that the flow is inviscid. This type of assumption can be used to explain aerodynamics and lift, or find the streamlines of a flow. The Reynolds number is also used to characterize turbulence. In a laminar flow, the fluids move in smooth layers, and this typically happens at very small Reynolds numbers. However, in turbulent flows, the fluid rapidly mixes and churns and moves in eddies and oscillations. Now, these high-frequency fluctuations make analysis difficult. In pipes, this transition occurs at a Reynolds number of about 2300. So below 2300, you have laminar flow. Above 2300, you actually have a transitional flow. And then for Reynolds numbers above 10,000 or so, you have fully turbulent behavior. If you have flat plates, the Reynolds number has to be larger than about 500,000 in order to have turbulent flow. So the limit depends on the geometry. Turbulence is actually one of the biggest challenges in engineering. We can predict it with direct numerical simulations. However, those simulations are very limited because they require a lot of computing power and a lot of time.